In this video, we will answer the question of why there is a phase lag between force and displacement in oscillating systems, why the phase delay at resonance is 90 degrees, and why it reaches 180 degrees in the case of decoupling. At the end of the video, I will show you two particularly relevant examples of how this phase shift can be used in everyday engineering practice. Imagine a dynamic system that can perform a vertical motion Z and is excited by an external harmonic force F. For linear, time-invariant systems, a harmonic input always leads to a harmonic output, but due to inertia and damping, this output occurs with a phase delay. The higher the excitation frequency relative to a natural frequency, this is so-called frequency ratio eta, the more the system response is delayed. Due to inertia, the system is not able to follow the excitation simultaneously and therefore reacts with a delay. At resonance, the phase shift is 90 degrees, and this is critical because, as can be clearly seen, the force occurs exactly at the moment when the velocity of the oscillator is at its maximum, and therefore the system is excited most strongly, and the energies superimpose in a maximally constructive way. In general, it can be stated that the faster the excitation, the more phase delay occurs in the system. If we visualize this, we see that with an increasing frequency ratio, we also obtain an increasing phase shift, which additionally depends on the damping. The response increasingly lags behind the excitation the faster the system is excited relative to its natural frequency. For a frequency ratio eta approaching infinity, the phase shift approaches 180 degrees, and we then speak of a decoupling of the system from the excitation. This phenomenon is utilized in practical applications throughout almost the entire field of mechanical engineering. If you want to learn to solve engineering problems like a professional engineer without unnecessary dry theory, check out the first link in the description, where you will find a bunch of interesting, real-world engineering exercises to learn machine dynamics properly. Two typical engineering applications where the phase delay is useful are resonance conveyors, where the conveyor belt is excited to resonance, and in this way components in factories or materials from construction sites are transported in an energy-efficient manner. In vibrating machines, tuned mass damper systems are often mounted on top in order to reduce operational vibrations by means of an absorber mass. The absorber mass oscillates with a phase shift of 180 degrees relative to the vibrating machine, and through destructive interference, the vibration of the machine is reduced in this way. In the upcoming video, I will show you how the phase lag is computed easily from the transfer function. Make sure you subscribe to not miss it.